pointers and putting function pointers into structs. And the main goal today is to help everybody understand project one. So the project one is quick and easy.
Cool.
Okay, so it's quick and easy. That's usually my thought on projects. The problem is that learning things is usually not quick and easy. Usually learning things actually involves some level of discomfort. And my daughter, who's now 11, feels this discomfort very strongly if she has to be introduced to a new mathematical or grammatical concept. You can see her struggling against the pain of the knowledge running into her brain. The odd thing is, she doesn't struggle in the slightest with learning something that involves physical pain, like learning how to kneeboard behind a boat or something like that, you know. Next day she's like, oh, I can't get out of bed, let's go again. You know, but not so with mathematical concepts. Anyway, so usually learning things isn't, that's actually kind of my least favorite part of doing any kind of a new project involving computers and engineering and things, is learning how to use whatever framework I'm supposed to be using for it. All right, now once you get through that, it's more fun. Which is a little bit, I guess, an issue with class, you know, like college, because I mean, I try not to repeat things too often. Some of the later assignments in this class are kind of more of a practice with kernel modules than anything else, and so perhaps those will be more fun. All right, structures and function pointers. So, I had this Scramblers demo. I think we should take a look at the Scramblers demo, but I think maybe first, well, let's go there first. Let's go there first. All right. I made this demo some number of times ago, and I don't think I particularly want to recreate it, but it's okay, it's around here. All right. So, Scramblers. Okay. So, I have a demo here that makes a couple of these things I'm calling Scramblers. And so we have actually a few of these Scramblers. We've got 4 of them in here. And we might add another one this time, and then each time I keep using a demo, we'll get more and more Scramblers until, you know, it's got a pretty rich collection. All right, so here's how this program works. Okay, so we've got the struct scramble right up here, and this defines a scrambler which changes words around. And so let me show you the effect of this thing maybe, and then we'll go through and see it. All right. So, we have giraffe up here given as an input word, and it's going to go through and print out a few different ways of scrambling giraffe. All right. So when we run it, you can see that we've got a few different permutations of it. Giraffe here, I think I have a null scrambler in here, like one that doesn't scramble anything. And then later, we unscramble it, and you can see it's unscrambled in every case. All right, so the SC1 is coming from this loop right here, so SP is drawn out of this array SP right here, which we generated using this function scrambles. Scrambles up here makes an array of scramble pointers, and then it runs each of our scramblers on it, which are stored in this array of scramblers, where scramblers rearrange words in various ways. So then up here, we have an array of struct scramble as our data type right here. Remember that with structs in C, you actually have 2 words for the data type. I realize that when we introduce C and C++, you kind of get this pattern that you say something like int x, so it promotes the idea that your data type here, that one's not very much better, is just 1 word. And so we're kind of changing that a little bit, since you might say something like struct, I don't know, this is a struct s. I don't know what a struct s is. But you end up with 2 words here. And some data types already have 2. So you can make like a long int x. You know, now your type is 2 words, right? In fact, you could even say it's a long int. Now you got 3 words. Maybe it's a const long int. So there's definitely a precedent here for having more than one word defined in type, and the types that are longer than one word. All right. So anyway, with a struct, you say struct whatever. That's one way to do it. You can also type def it if you want to make the struct a kind of one-word thing. I'll show you type def soon enough because there is one in project 1. All right, so struct scramble is the type here, and scramblers is going to be an array because we have the brackets right there. You don't have to specify the size there. We could say 4, or we could say more than 4 actually. Isn't that working?
It's typing down on the phone.
We could say 4 there if we wanted to. If we said like 10, we'd make an array that was 10 items long, but we'd only populate the first 4. I guess it would waste memory unless we intended to use it later. But if you just leave those out, the compiler will figure it out for you if you have a list of initial data for the array. Because then it knows how many items are in that list, and it can figure out the 4 for us. All right, kind of more handy to do it that way, because then if we add something, we don't have to go through and put a new number there. All right, so 4 items here are called shifts, reverser, end swap, and do nothing. That's kind of the null scrambler, the scrambler that doesn't scramble. And so they kind of do what they, I guess, say to some extent. The do nothing one up here has copy and copy as the actions that it performs. When you make a struct, you can if you want to. So this is a struct scramble. You notice it's actually a const struct scramble. And it's not an array, it's just a single variable. And we're going to initialize it using the curly braces there, like it was an array. You can do that with a struct. The struct up here, struct scramble, is defined right here. It's got exactly 2 members. And so when you do something like this, you're just giving a value to each of those 2 members. The same one in this case. The first 3 here are the same. This one's different right there. All right. So what are the 2 values supposed to be on a scrambler? All right, sometimes when kids are in restaurants and there's a wait for food, it's very important that some sort of entertainment be provided. Kids are very good at creating their own entertainment, but sometimes that entertainment is not necessarily desirable in a restaurant. Oftentimes the kids will be provided with a placemat, and one thing it may have on it is a word scramble, where you've taken a word and rearranged the various letters, and then it's entertaining to figure out what the original word was. Why is that entertaining? I'm not quite sure, but it is. Anyway, that's what these things are generating. We have a way to run the scramble, but we also need to have a way to undo it. So undo is the opposite of what run does. Now, sometimes when you do something twice, you end up with the same result. Now, if I take this pen and reverse its direction, and I take this pen and reverse its direction, I've done the same thing. I did it, and then I undid it. So sometimes run and undo are the same, and sometimes they're not. All right. So the data type on these. We have char star right here. This is the return type for the function that's going to comprise this member. This is going to be a pointer to a function. We pretty well always use pointers when passing around functions. The reason is the code for the program is going to be in the code segment in the program's memory. And usually we don't want to duplicate the code for a function and copy it somewhere else. So normally when we're passing around a function, what we're passing around is the address of the function inside the code segment of the program. Very seldom do we actually copy the code around. Although I guess in 475 we're going to try to put code on the stack. All right, anyway, there we go. All right, so we're going to have the memory address of the function, and that function is going to take a single character pointer as its parameter. All right, so they both have the exact same profile here. Basically, they take a string and return a string. And these functions here, shift, unshift, reverse, first, last, copy, they all follow that exact same plan here. Copy, for example, we go ahead and allocate the size of a character. We don't really have to, it's 1. Size of a character times the length of our word plus 1. to make sure we have room for a null terminator, although I think, come to think of it, strlen might return null terminator. We may be over allocating by one character there. And then after that, we're copying our word into our new string here and returning a string there. All right, so it makes a copy of a string that's on the heap. Okay, so for the do nothing one here, copy is what we use. All right, now this program, we're calling free on these usually. Yeah, I think we're diligent about calling free. I bet Valgrind will agree that it frees all of its memory eventually. But when you make something on a heap like this, you do have to be careful to free it later. So these functions pass the responsibility for freeing this word onto whoever calls the function, because they return a pointer that's going to need to be freed later. All right, first last on the other hand, does the same thing, but then we reverse the first and last character of the string. So the reason this works, normally when you swap, you end up with 3 lines, because you have to put the value off into a temporary. But since we have the original word around, we can just go ahead and copy the last letter in the word to the first letter in what we're producing from it, and then the first letter in the word, the last letter of the thing that we're going to be outputting here. All right, no need for a temporary or anything like that. All right, reverse. So instead of strcpy and copying the whole thing, we just go ahead and allocate our spot for everything to be reversed, and then in our loop here we copy everything across in reverse order. Being careful to put a null terminator at the end of our reverse string, since that won't actually naturally happen. If we were to include the null in our reversing and put it at the beginning, that would be kind of a problem actually. So we don't want to do that. All right, and then shift and unshift. These ones just shift all the letters over. So if we look at the output here, instead of giraffe, you see E has been put at the beginning instead of the end. So it just shifts places on everything. All right.
The second one's completely reversed.
Yeah, the reverse one from this one. Yeah, so anyway, shift and unshift are kind of the same but opposite. It could have probably been parameterized in some way, and then both of them could call some common function, but that's not the way I put this together. All right, so, well, you saw what they did. We don't necessarily need to go through them.
Did you say every time you have a function that is like a pointer, you have to clear memory, or?
Function is a parameter for this
like
kind of
the try, star, or shift, maybe or the shift, whichever one.
Oh,
It's like a function pointer?
so it's returning, the star there, that one should probably be actually over here. It's the return type of the function.
Yeah.
And so the char star describes, it's the memory address of a string, and so basically we're returning a string.
She was asking about what you said earlier about if you use a pointer to a function that you free up the memory.
Oh yeah, all right. So we got malloc called in each of these things. And so malloc is going to return some memory that we're going to store the address of in shifted and in return shifted. So if we didn't free this later, we would be losing some memory. So if I left off, say, right here, this is where we unscramble them. If I leave this off, probably had Vim in not the right mode there. All right, it will actually run fine. I'm going to put the debug thing symbols into it. As far as we can tell here, we're fine. But if I run Valgrind, you can see heap summary, leak summary definitely lost. So we held a memory leak. Yeah. All right, so there's all of those. Okay, so once we've got our list here with each of these scrambler structs in it, then we get down to scrambles here. And so scrambles runs each of the scramblers on a particular word, and then it returns an array of pointers. So our scrambles here is something we can iterate through right here. SP is the name of our result there, and so we can go through and print each scramble, right, just like this. Okay, so the reason for the double star there, the scramble pointers is going to be an array of 4 memory addresses. Each of those addresses is the address of a string. So we've got, when you think about pointing at the beginning of the array, we've got a pointer to a list of pointers to characters. So that's where we get char star star.
Double pointer.
Yeah. When you have an array of pointers, you've got a double pointer. You can also have like a single double pointer, like the address of some pointer. But in this case, it's an array. It's actually the same data type we see with like argv for giving parameters to main. You have like arg c char star star argv, that kind of thing. All right. Okay, so I'm going to run through and run each of these things. Okay, so in C++, we talk a lot about object-oriented hierarchies and having more than one type of object that has different methods. And so you could actually have a list of objects, and you could declare your list of objects to be whatever the base class is. And then when you call some function on them, the function might actually be a different function depending on which object it is. I'll use the same example as 311, and then anybody that's in that class will immediately recognize it. All right, so if I go to current, I have this game engine here. All right, let's look at the main loop real quick, for the drawing loop. This is the drawing loop. And so for each object, and these are all base type game object, we're going to call this draw method. However, the game has like teapots and brick walls and a box with pictures of a monster on the sides of it and stuff like that. And so the draw doesn't actually, it's not actually the same function for every object in the list. As it goes through, it's going to be doing a different one. Kind of like, you know, if you walk up to like a table, and on the table you've got like a cat and a rattlesnake and a mosquito, and you call the bite method on each of them, something different will happen, right?
Hopefully.
All right, so we're going to run through these, and each of them are going to do a different draw there. So over in our scrambling, when we run through this, for each of these scramblers, we're actually going to be running a different function. So we're essentially accomplishing the same kind of thing as we would in C++ when we use inheritance. This is the C equivalent of doing that. All right, it's used a great deal in the kernel for stuff like our file operations example that I was talking about the other day, where if we decide to print out a file, we're going to be calling a different function in the kernel depending on what sort of file system the file is stored on. The file is stored on a CD. We're going to be calling a function that finds files inside ISO 9660 file systems. But if we call it one-on-one on a hard drive, it's going to be like, you know, ext4 or something. Hi, there's a spider. Does it have a bite method? Mm-hmm. Oh, I can't put it out the door over there. There's a door. I moved the spider out the door, except that
Set off an alarm.
yeah. All right, I'll put the spider right next to the door. Maybe you'll figure out how to get
Right
out.
on the handle for the
Someone
next
will be
person.
trying to exit.
Set
Yeah.
a trap.
Yeah, it was a safe spider. It's not going to hurt anybody.
It's a spider set. There's no safe spider.
Well, I mean, it depends which kind of spider, you know?
Yeah, it's
I
not
mean-
a hobo.
I mean, if you find a black widow under your bed, you know, you're like, oh, I'm really sorry. And then you squish it, you know?
But if it's a jumping spider, you take it outside.
Yeah, and it can go jump on something else. Yeah. All right. It's not the black widow's fault. It's just, you know, my neighbor got bit by one.
Oh, that sucks.
Yeah, he said it was it induced this like weird paranoia for weeks afterwards. And he looked it up, and apparently the venom it does affect your brain, and it's a reasonably common symptom of it is to just have like this paranoia that won't go away.
Dang. I did not know that. I knew it was pretty painful though, but most often not fatal.
Yeah, he said that was the worst part. I believe he said his brother got bit by one and kind of corroborated that.
So he basically haunts you after you die.
Yeah. Yeah, they're usually non-fatal. Black widows. No. All right. So oh yeah, so we run a little bit different method on each of these things. And so this is kind of our equivalent of doing like inheritance. So the kernel is very object oriented. It's just that, so the entire point of doing object orientation, the way C++ does it, is to free the programmer from having to think about the details of exactly what everything is. You can go ahead and call methods on something without understanding exactly what type the method expects or what exactly you're doing. In the kernel, the developers do not want to relieve the programmers of the kernel of the burden of understanding exactly what they are doing. All right. And in a way that sounds good. I mean, you can imagine some cranky old programmer being like, nobody who doesn't understand what's at every memory address has any business writing a program. But the fact is, that's not necessarily a useful attitude for every program. There's plenty of programs where you should just go ahead and expediently get it done and be done. And there's also plenty of programs where if you have to understand the layout of every last bit of memory, you're going to have so many things in your head that you're maybe even more likely to make some other kind of bug. So it's not necessarily an argument that applies to every bit of code, but it does apply to kernel development. All right. There we go. And eventually we'll return this array of scramble pointers. Notice that we use malloc there, so we're going to have to use free later. All right. We go ahead and generate all the scrambles for giraffe right up here. And then this in_scrambles variable, have that hound defined up here. Figures out the number of scrambles that we have. We could make that process more automatic, easy enough, by just having it defined as, say, the size of this scrambler's array divided by the size of an individual scrambler. We did that in, a different class in 311. All right, I can't tell the classes apart. All right, there we go. So then down here, we're just going to go ahead and print out each of our scramblers. We'll just make kind of a loop here and go through each one. This is the kind of the next bit there. It's sort of redundant in a way. It's this bit right here. Print it out. All right, and then down here we've got these the unscrambling, and so we'll go ahead and unscramble piecemeal. So the unscramble here is scramblers I.undo. We're going to call the undo scrambler from these at this particular spot. Now notice also that we're actually using the same kind of syntax here that we use for a C++ method. We've got scramblers at position I.undo. Undo is a function, and here we use it right there, like it's a method. All right, but if we were in C++ and say this shift here were actually a method, then we would also have this, like a struct scramble star this available to us. We don't have that. So it's not the same as a C++ method here. Since we don't have a struct scramble this, we can't just go ahead and mix in some data right up here and expect to have it available. Suppose we had something up here. We had like int important thing, all right, as a method there, and we're going to call this. Well, we don't have a this pointer, and we have to have it explicitly passed in. Struct scramble full star this. All right, then we could say this arrow import. I don't think I spelled that right, but whatever.
Yeah.
All right, so you get the point there. If we wanted something like a this pointer, we'd have to declare it in our parameter list and specifically pass it in. We could do that. We could name it this if we wanted to. I don't think that's reserved in C. All right. Okay, so I talk about abstract data types in classes like 311, which I'm actually teaching for the very first time this fall. But I've taught almost the same class as CS something else at WSU, so I feel somewhat familiar with the thing. Anyway, I talk about abstract data types. And an abstract data type combines the operations and the data together. Well, we could, but our operations would have to have an explicit pass of the data into them. All right, and you do actually see that sometimes. I should have looked this one up, because I didn't actually even think about giving this example while I put together my notes. I never really do. Like I'm up here, and I'm like, wait a minute, I know a better example than I thought of. Where is that thing? All right. Source for report on 19. All right. Let's go to the stuff that deals with files. All right. Okay, so we talked about file operations before. You're familiar with file operations. There's inode operations. All right, so here's one way that this sort of stuff is sometimes structured. If you look at an inode operation, an inode represents a file, more or less. We'll talk in more detail about inodes, but essentially an inode is a thing that is usually used in directories to represent a spot in a directory structure that's oftentimes a file. All right, one thing we can do is look stuff up, and this inode operations operation here, lookup, requires a struct inode as this very first thing that's passed in. So inode operations is a collection of operations that, for the most part, are actually going to take an inode as their parameter. Not every last one does. Well, there, that one doesn't. Read link. It takes a directory entry, not an inode. But most of these things do have a struct inode as their first pointer. So they've separated out the operations into one struct, and then the struct inode has the data relating to these. All right, let's take a look at struct inode. So here's a struct inode, and so this mostly has the data in it. So any function, any pointer is a union. I've seen a pattern sometimes where you actually do see a pointer to a function in here that takes the thing that you have there as a parameter at the beginning. Maybe not inode. Here's the file operations for the inode. So you have an inode that's inside a file system somewhere, and so you'll have the file operations for that file system associated with that particular inode. All right, don't see it. Okay, well, sometime or other, I'll find you a function, or excuse me, a struct that has a function pointer in it that takes as one of its parameters the actual struct that it is inside. I've seen a few of them before. I just can't remember off the top of my head where one is.
Probably had a couple in our scavenger hunting.
Possible. Yeah, he could have, definitely. All right. Well, anyway, I was hoping to just find a random one here. I think when we're into the memory stuff, we may just kind of run into one, and at that point, I'll forgot I ever intended to show you one. Nice. Let me make sure this is working. Yeah, they're connected.
Looks
Is that
good.
working? Nothing in chat. Nothing like it's broken. All right. There's kind of an example of structs and function pointers and how this sort of thing goes through. All right, we keep using file operations as an example of how this kind of thing is used, and there's a lot of other ones in the current. I just showed you inode operations, which has the same kind of pattern as file operations, and so there's plenty of other ones that have similar sets of operations that happen on stuff. And so you see a lot of places where a bunch of function pointers are stashed in something. If we go over here, let's pop over here. All right, there's a lot of files in here, and I haven't actually looked at probably most of these things. What about a networking one? I have a wireless.h. It's in wireless.h. All right, that's a bad choice. Because I didn't see one. It was really short. That's really short. All right. See that? Short. It's got a struct in it. With a randomized layout.
Weird.
Like yam.h. I didn't notice in yam.h. All right. Maybe I'm not doing a very good job explaining my point about function pointers and ones. We have seen an awful lot of structs here, though. You can see that there's a pretty common keyword to use in here. And so you can see it's going to be important. All right. What's this? Enum. So one of the following. All right. There's various structs there, but there we go. There's another one. Hey, I might have just no, that's IRQ data. All right. So this IRQ chip struct has a struct device parent device in here, and a name, and so it actually has some data members, and then it's got a whole bunch of function pointers, and then it's got some flags. All right, what's this called? IRQ chip. Now, all of these things take an IRQ data, so it doesn't have exactly what I was looking for, but lots of inline functions.
Okay, so in if you're on Linux source 4.19 and the include /sound
All right.
/core.h
Includes.
line 75.
All right, did you say 4?
Core,
Oh, core.
C-O-R-E. Yeah.
Line 475?
Line 75.
Oh, 75.
I think that's what we needed. Oh, never mind, that's a send device. Okay.
Yeah, close, close. I think I did actually find one in Linux and whatever that file was I was in a minute ago, irq.h. So, right here, struct IRQ chip generic has some members, this suspend and resume functions, and suspend and resume each take a struct IRQ chip generic pointer. It's essentially a this pointer. They haven't named it that. So in, because like in C++, you have a pointer called this that refers to your actual instance of the object that you're dealing with. Now in here, either the person calling suspend or resume is free to pass any struct IRQ chip generic pointer into it that they have. But I would think that that function probably treats it as a this. In some ways it doesn't necessarily matter. I mean, they could have instead just made a function that's not part of the struct and named it something like IRQ chip generic suspend or something like that. And you just call it an IRQ chip generic without it being part of the struct.
And this is the same as self from Python.
Yeah.
So that's what it's.
But although if we did that, you couldn't use a different suspend function for different struct IRQ chip generics. So actually, come to think of it, they couldn't do that. All right, I take back what I just said. It kind of has to be in there. All right, so there's a mix of data and methods together. So I think what we have there is an abstract data type written in C. All right. Boy, star private.
Okay.
Vim went ahead and syntax highlighted it for us. I'm not sure where they hold in that memory address. I don't think we get to know.
Yeah.
All right. It actually has a kind of an explanation to what each of these things do. You can see suspend here is a function called from forward code on suspend once per chip. Can be useful instead of IRQ chip suspend to handle chip details even when no interrupts are in use. So actually, yeah, they are using it to give a more specific suspend routine for this particular chip to handle that chip's details. All right. Resume looks kind of like the same thing.
Same thing.
Yeah. All right. The file operations is pretty typical, but sometimes you see the data and the operations in the same one. I think with the file operations, they just decided to organize things by having the file data in one struct and the operations in a different one. But obviously that's not universal. Okay, let's take a look at the project one before we go on to the next part right there. Okay, so let me download project one again. 430. All right, so there should be a bundle right there. Zip archive of these things. Let me copy link and let me grab it. All right, so there it is. All right, so it has a make file in here. If we make it, should hopefully build. And it's not yet out, project one. this last line here combines it together and it actually names the output project 1. Alright, doesn't print out anything yet. Okay, so let's take a look at maybe tester dots. Well, let's start on tester.c. Okay, so this is the tester, and it tests to see if you've made a bundle that works correctly. Alright, so let's take a look at what a bundle is. That would be in tester.h. And here's what a bundle is. So I went ahead and used the type def here. They're not that common in the kernel, but they are used occasionally, so I'm going to make sure you know what they are. So this assignment has one in it. Alright, so a struct bundle struct here has 3 functions in it: find best, sorted copy, and combine. So then this test function here, we've got a prototype for it, function we were just looking at. It requires the address of a bundle in order to operate, and it'll test to see if the bundle's correct. Alright, so you should know if your program works before you turn it in. You keep working on it until it does.
Thanks.
Alright, so over here in the tester.c, we got a lot of stuff that bundles are supposed to do. For example, it's going to call find best on B, which is what it's named the bundle right up there. It's going to run sorted copy on it, and it's eventually going to return the last one, combine there. So it'll test out each of the functions that should be in the bundle. So inside solution.c, you can see why it doesn't print anything in here. You want to call the test function inside main here, but you also need to assemble a bundle of functions and be ready to hand them over to it. Alright, so let's take a look at what the functions do. There should be a kind of a description on here. Alright, so find best takes 3 parameters. The first is a list of functions. The second is a parameter for calling functions from the list, like when we're going to give to each function when we call it. And the third is the number of functions in the list, just how many are there. Alright. When we look in tester.c here, there's find best. And one note about this thing, let's go to tester.h. I've got the list of functions specified as a void star. So you're going to have to cast it to a more appropriate type before you can call the functions in the list. Because you just get a memory address, and you know it's at the memory address. You can do some casting and make this work. But it doesn't have the type predefined here. So inside find best, you're going to have to cast the first parameter to something different. Alright, so here's tester.c. Now, this might give you a good hint about what you should cast it at, what we're actually giving it for the first parameter. We're going to make this array of returners. These are functions that are going to return something or other. And so that's the first parameter, this list of functions. Then 23 is the parameter that should be given to each function when it runs. And then 10 is the number of functions that are in the list. Alright, so we'll actually run it with C1 and get back C1. But we'll run it again for this integer C2. And it'll be the same list of functions, but this time we're being given the parameter 77 instead of the parameter 23. Alright, then after that, we go ahead and check and see if the results are as expected. And if they are, then find best apparently works. Cool. Otherwise, it doesn't. And so we mark done as false here. Alright. These macros here, this whole fill business. A lot of times people ask about macros when they get to this project. So they're not a huge topic in C++. In C++, they're not usually the first solution that's brought up for a problem. They're more frequent in C. That said, they work fine in C++, and you do see them in C++ for sure. It's just not the first axe out of the shed. All right, so let's make a quick macro. I probably, I might have one. All right, we'll pop D over here. Oh, I don't have a demo called that. Oh, I might. All right, that's okay. Make one. All right. Define. I don't know. Okay. There's a macro. See if this works. O.c. There we go. Hi. Okay. So you can define one thing as another thing up there. Let's do. So we define gerbil as that. Fine. What's
The
that?
macros go, like, say you had gerbil inside your string literal, would it be interpreted as a macro, or would it just interpret it as a string?
I think it'll still just interpret it as a string, but I'm wrong. Or no, I'm right.
Yeah.
Sorry.
If it's outside the quotes, it'll pick it up as a macro, but.
Yeah, yeah. No, it actually it came out there. Okay. So you can have parameters. Printf. All right. So I don't think this creates a weird loop or anything. I think we're okay. And we're going to find printf as puts. Well, let's go gerbil. We already have that. And we'll say printing out S because we have to. All right. And then we'll go ahead and add whatever the user gave us. So we need an argument. Printf x.
Your parentheses there on the end. Need 6. Oh,
Yeah,
okay,
there we go. All right. Printf. Morning. All right. So what happens there? I suppose there's a new line at the end of this one too, actually. Okay. There you just said printf good morning. There. So you see now printf is just kind of replaced by this thing here. And so anyway, a macro allows you to do a text substitution before the program's compiled. The preprocessor interprets this and runs through and does whatever the macro says to do. So there's some things you can't define away, but there's an awful lot of stuff you can that you can actually change. And so if you wanted to say something like define, and we'll say that int is actually a float. I don't think it's necessarily going to stop you. We build it, it ran. I'm not sure it really changed anything. But the macro will allow you to change stuff like that. So sometimes you might want to use a macro instead of a function if what you really wanted to do is, say, encode a formula in something that's not going to have to run every time. You're just like, all right, I'm tired of typing this formula. Maybe instead of a function, I'll just go ahead and use a macro. They can be used for things like that. But they can also generate complete functions. I noticed that I had something here called macros, plural.c. So apparently this is some of what I did before. So x and y are actually char stars, like strings. And then puts there is just going to print them out. And then for loop is actually called funny, or it's a funny loop instead of a for loop. And we had to use a short for the counter there because we couldn't say int. If we said int, we'd have a char star I.
Mm-hmm. You could really make your code obscure and hard to read.
Yes, you can. Yeah, you can make your code very obscure and hard to read using macros.
Cool.
All right, yeah. It definitely is a good factor in the obfuscated C code contest. Okay, so inside the kernel, these things are used really pretty often. User associated Linux source 4.19 again. All right. Linux. All right. So you can see a lot of things that are just numbers that are defined. But if we keep looking through here, we'll see stuff like wake up. is defined as, see, it's kind of like, it looks like a function here, wake up x. What we're calling is wake up with 2 underscores in front of it, and we're giving it the parameter x, but we're also giving it task normal, 1, and null. So basically they're using this to give a wake up function. It calls some probably more flexible function. It does more things and takes more parameters, and just encoding the parameters right in there. All right, there's actually a number, and you can see that this double underscore wake up is used a bunch of times with different parameters, depending on which one of these wake up permutations is actually being called. All right, apparently update screen is the same thing as redraw screen given a parameter 0, and switch screen is the same thing as redraw screen given a parameter of 1. All right, so in a lot of cases they're used to provide a little bit more convenient user interface to things. Some of them I probably have to go open up to figure out, anyway, lots of use of them. Fine. So you can see the most common usage here is just stuff like this. vExpress site MB is defined as 0, so it gives you constants. But, you know, like find closest here, we've got find closest, and it takes a few parameters, and what we're actually calling is double underscore find closest, which is some other find closest function. You see this pattern fairly regularly, actually, where the user of the code, like the person including util macros.h, is presented with a function, or what looks like a function like this, but actually it's a macro calling a more complicated function somewhere.
Why do they have certain things defined as nothing, like that define underscore double underscore Linux USB H?
So it's probably like an if tag, right?
It is probably used later. We can say if this is already defined, don't actually run through the header file usb.h again.
Okay.
So you don't double include something. Because it could be that, say you include usb.h, and then you pound include something that includes usb.h, you don't want a second copy of usb.h. So I can check and see has that been defined, and if it's defined, let's go ahead and skip it. If we look at usb.h, I'm guessing that right after that, so we're saying if usb.h is not defined, go ahead and define it, and then we keep doing all this stuff. So down at the very end, we're going to have an end if that actually ends that if statement. We've got 3 of them, but that's probably the one ending that particular one. You can see that one there is ending this if def right there, and they have actually marked what one this is ending, probably because they were like, we're going to have 3 end ifs on the end. We need to at least mark something about what's going on here. So that's probably the end if that matches the if not defined right up at the top. You'll see that pattern in a lot of these ones. I keep talking about fs.h, you know, there's the same pattern right up there. Yeah.
Nice.
Yeah, have a good observation.
So are they trying to support like more compilers out there? Could they just use like Pragma once instead, or like?
They pretty much just support GCC as the compiler. It's gotten tied to GCC enough that it doesn't build on Clang and things like that. Some of the stuff that they use is not strictly in the C standard. Usually things where they're giving the compiler some directive about how to lay out memory in some area or stuff like that. Like we actually want this one randomized or whatever. Yeah. Clang is reasonably compatible with GCC for most purposes, but I don't know if there's necessarily a goal to support it in the future. Alright, so there's a few pound defines and some things that they're used for. So in tester.c, we've got this macro here, and it's given 2 parameters, y and x. Why are they in that order? I don't remember. I guess that's the way I wrote it. So each of these is going to be named, is going to define a function right here. So if we try to expand this thing out, what we're going to get is int r pound, and then x is whatever we give it. So I'm going to say what we call fill, and we'll give it something like, oh, I don't know, return, we'll just go ahead and do one of the return ones. We'll go ahead and expand this one. All right. I'll be careful not to save it, because I actually did just remove that. All right, so x there will be 10. So we get 10. And then we get this opening brace. No, we get int x. And then we get the opening brace, return 1 or 10,000 minus. All right, lowercase x is our parameter right there. Uppercase x is the macros parameter. So that macro parameter was 10 times x minus 10, 3 closing parentheses. Did I make a mistake about openers? Yeah, I did in this one. I'm being a bad preprocessor. All right, then a semicolon, then a closing brace, then a space. Then we have y up here. Parameter y we said was going to be returners as position 0. And then we have an equal sign, and then we have r, pound, pound. And then we have this, x here, which is our second parameter, second 10. All right, so that's what it turns into. If we go ahead and syntax, put this into normal spots, it's going to end up looking like that. You don't necessarily need the new lines like for the compiler, but it sure looks nicer to us. So what we've essentially done is define a function. I'm calling this R10. And then we've assigned it into the first item of the array of function pointers called returners. All right. And so the reason for this macro is because I didn't want to have to type this repeatedly. All right. So hopefully that makes sense on the fill macro. Basically, it's filling this array with functions. All right. Notice that the functions are actually defined inside the function test. That's okay in C. It's not okay in C++. If I were to just this make file and say that the compiler is G++, and that we're going to say the standard is, I don't know, C++ 11 or something like that. It's save thing and remake it.
Not gonna like
it. No, we're not going to be building this thing in C++. All right. I think I was building it in C99 before. There's a newer C standard. I think it is C11. Let's see. Yeah, it's happy to build it that way. All right. Yeah, macros. Always fun. Okay. So where are we next on S? Oh yeah, bitwise. And doing bitwise arithmetic. And OR and whatnot. Not too much on exclusive OR, although we're going to talk about exclusive OR and cryptography if you happen to be in that class pretty soon. It's okay, we don't have to talk about that one. All right, so usually you see and OR when using bitwise arithmetic. And so these are commonly used for things like setting flags. If you have some number and it's going to indicate a bunch of different possible things, the minimum amount of memory for a true or false value is a bit. It can be 0 or 1, true or false. So, since the minimum we can allocate in our compiler is a byte, that's kind of an inefficient way to store true and false values. We don't necessarily need to allocate 8 bits to store true or false. So a lot of times when there's a bunch of flags that are needed, they're put together into one. And so you'll have something like a flags variable, and so then each of these individual flags, each bit will have some meaning. And we've seen this a number of times in stuff like file permissions. So like with file permissions, what we see on Unix type systems is read, write, execute. And so if you have a file that you can read to and you can write to, but you can't execute, then this is 6. Yeah, the 4 and the 2 together, you get 6. All right, so probably familiar with that kind of thing. But then, how you set this flag, suppose you're not on the command line anymore, and you want to add execute to this file permission. So you don't want to add anything else. All right, so execute, there's execute right there. And adding things together like this in a numeric sense is not quite always what you want. What if you want to set this, but you're not quite sure what this value is right here? Well, if you were to say plus and just add these things, you know, you could get what you want, but you could also, if this was actually a 1, end up with this being a 0, carry the 1, this becomes a 0, carry the 1, this becomes a 0, and then you get a 1 over here.
That's the whole thing.
Yeah, so you don't want to add these. That's not the right operation here. All right, none of that. Okay, so you actually want it as a bitwise OR. Put a little gap in there, because it has a little gap in the symbol on the keyboard for it, the one underneath the backspace on most keyboards. You just use one of them instead of two. And so is this one, you know, one of these is true, one of these is true, one of these is true, so that's what you're left with. And it doesn't matter what that was. You don't have to know. All right, so that's kind of important there, in that it preserves the originals and doesn't require you to actually know what you've got. All right, so then unsetting one. Suppose we're not doing this anymore. We have something, and say we don't know what this one is, but we want to make sure it's not set. You know, whatever it is, it needs to be a 0 afterwards. Let's say this is 0 too, so we have one of each there. All right, so if we take a 1 and a 1 there, and a 0 here, and then take an and, the ampersand, single and, the bitwise and. We're going to go through here, and both of these are true. Both of these are not true. I mean, regardless of what this one is, they're not both true because that one's a 0. And, well, they're not both true. So what we end up with is whatever was up here, except for this place where we put a 0, and there we unset that one. So we end up taking it away. All right. Probably the most common use you see for the bitwise operations inside the kernel. There are other places we use other stuff like bit shifts. Actually, bit shifts are reasonably common. So the bit shift moves things over by one place. So let me show you one here. We'll make one real quick. All right. Oh, I have a bitwise demo. All right, but it doesn't have a shift in it. I have a not one on there. That's good. I was going to have a not. All right. Although knots are sometimes one of the sleepiest ones. All right. So right up here, take a look at this. We got 3 shifted over by 2. So let's go ahead and run this, and we'll see what comes out. All right. Looks like I'm also doing some bitwise ands and stuff up there. But all right. So the second line down there, we got a C. All right, we're printing this out in hex. We can also print it out in decimal if we wanted. And so we should get a 12 in decimal.
Yep.
12. All right, so here's what's happening. So we got a 3 and we're shifting over by 2. So we take a 3. All right, this is the 1's place, 2's, 4's, 8's, 16's, 32's. We didn't have to go that far. That's a 3, with the rest of it being 0. All right, so if we shift it over by a place, and you know, we're going to end up with this. So that should be a bit shift of 1, and you can see that'd be 6. All right, but we're going 2 places, not 1. So you go 1 more place, and we're going to end up right there. So if we've ended up right there, we've got an 8 and a 4, that makes 12, or C. All right, so one thing you can actually do with these bit shifts and ands is come up with a way to print numbers in binary. All right, so I got a quick binary printer here. All right. So for printing in binary, we'll go ahead and take some kind of input number. So I'll say like int start number equals maybe something where we can figure it out, something in hex. I mean, all numbers can be expressed in hex. It's just kind of easier in binary to work with hex. All right, we'll go with something like, I'll go for C, and so we already saw what C is, the 8 and the 4, nothing else, followed by 3. Well, we already saw what that is, it's the 2 and 1. All right, so then what we have to, our challenge here is to run through and print the bits from highest to lowest as we go, that direction. All right, so we can take and start checking to see if these things are true. So if we wanted to know if the first one's true, we could say something like if start number and maybe well 0x80. All right, 0x80 there would give us a so we're looking at here with the hex characters. Our first one, that's the hex character 0. Second one, we're going to be looking at a 1 right there. And so this is 0x 80, like that, just a 1 all the way over on that far side. All right, so if we say take our start number and it with that, do we end up with a 1 there or not? So this will ignore everything else in start number. Since all the rest of these things are 0, it doesn't matter if they're true in start number or not true in start number. All right, so if that's true, we can go ahead and print out a 1. All right, cool. So we can go ahead and do this. It's going to be a little laborious. We're going to automate this. 4, 2, 1. And so our first one up there is a C. All right. Okay, second one. Let's take out the zeros. Don't worry, we won't leave it like this. This is kind of dumb. All right. So there we go. We've ANDed it with each of the numbers counting down in turn. So let's see if this prints it out in binary. All right.
Do else print 0 for each of these? Because otherwise.
Yeah, good point. All right. Now it's even longer. All right, I'm going to start from the end because when you start pasting,
Nice.
when you start pasting the other direction, you
It's easier
move
to
stuff
get mixed
around.
up, yeah.
Print binary. Let's see. Hey, that's even what we expected. So we got 0xC3, I think I said. All right. The last byte down there, those last 4, well, that's 3. And then this one is C. That's a 12. All right, so it worked. In a super cumbersome way. All right, so what about bit shifting? You see how we've got this start number and this 8 here. And so the 8 is simply a 1 right there. But if we just kept shifting it down, then we can kind of move our 1 along. All right, so make some kind of loop, and I'll have some kind of, sometimes you call this a mask. Here's why I call it a mask. It blocks everything except our little hole there where the 1 is. That's the only place we can see through. All right, so mask equals 0x80. We'll start out with our bit on the far side there. And what we want to keep doing is saying mask is going to have everything shifted over. No, it's that way. All right. Shifted over by 1. So we'll keep repeating as long as our mask isn't 0. Because if our mask is 0, we're done. We're going to go ahead and do our little if statement here. All right. And instead of this, we're going to do mask. All right. Okay, that should be indented right. All right, so that'll wander over, and let's see what happens.
I think you might have forgot a semicolon.
Yep, it appears so, right there. Whoa, that's not what I expected. What's going on there? Oh, did I go the wrong way?
Yeah.
That's it. I forgot the new line at the end. All right, so if we wanted to condense this down and be a little shorter, we could say, here, make the next version. Alright. A lot of times in the kernel, programmers are somewhat into condensing things. What happened there?
I was wondering why you had that one hanging out. There's another one because you copied it.
You're right. What did I do? Alright. That's fine now. Alright, we don't necessarily have to do all these things. We can say printf, say start, number, and mask. One. One more. Otherwise, 0. Alright. I put a question mark in the wrong spot. There we go. So that'll be a little shorter. I'll use this space right there. See if that does the same thing.
Yep.
Did nothing?
Oh, it worked.
Well, I should have a third one down there.
Oh.
Not sure what went on. Oh, I didn't reset mask. That was a really important part of it. Mask has to be reset. Mask started out at 0, so skip the entire loop. Alright, reset mask. There we go.
There you go.
Alright, so yes, it can continue to be made shorter and shorter, and we could probably convert to a do while, and I bet the result of that operator right here is the actual value of mask. So we could say something like do all that while mask 1. I think you put a semicolon there on do while. There, now it's one line shorter. There, it's the same thing. Alright. We shorten more. It's a fun game, but not particularly a super important part of the class. Okay. Alright, so there's a use of a mask to go ahead and just print stuff out in binary. So if you ever need to print stuff out in binary, you can grab these 5 lines here, and it does seem to work. You have to start this wherever you want it to for your number
Whatever
there.
yeah.
If you're printing out more than a byte in binary, you just need to make that bigger. Alright, so sure, there's a brief review of a bit shift and an example application actually. Alright. So we did that. We talked about logical and bitwise. Mentioned those are the most common. I would say that's probably true, but it doesn't necessarily mean that the others aren't anywhere in there. I noticed my little demo here, the one we looked at before, bitwise.c, had a not right here. Not 3 equals something. Printed out in text. There's not 3. Alright. So let's take a look at not 3. Alright, that's not 3. Yeah, this is not, right? But here's what it means. We went ahead and set all the bits on this number here, which I think we had an unsigned int maybe. It's put %sign x, so printf is expecting an unsigned int. Alright, so to set all the bits in our unsigned int to 1, except for 1 and 2, like the first 2 bits. So those ones are not set there. So the not there sets all the bits except the ones that you specify as true. Basically, it flips them all opposite what they were before. Yeah, that's not 3. Okay, this is the bitwise not. The exclamation mark is the logical not. They mean a lot of different things. Okay. So if you wanted to reverse some flags completely, you could use this one. Notice that this is also the same tilde that's used for the destructor in C++. So there's an awful lot of redundant symbols. You know, it really would have been better if the dominant language for programming had more symbols in it than English uses. Because we've got all these repeats, where we've got 3 different meanings for the same symbol.
Does get a little confusing at times.
Right, and a lot of times there's some kind of relation, like the ampersand means and in English, and so the double ampersand is the logical and, the single ampersand is the other one. But, I mean, like, what about the star? You know, what's star mean in English? Even a footnote, if you're reading a textbook, if you use a star, you look for a footnote later. But that doesn't have anything to do with memory addresses.
Or
I guess maybe you're saying that
multiplication.
this word is a pointer to a footnote.
First they had to make it multiplication because you can't use an X.
Right. Yeah, anyway, we're kind of, you know, oddly enough, I don't think the at symbol means anything in C that I can think
I
of.
should have used it.
Everything else means something. What is dollar sign? I'm not sure dollar sign
I've
does.
used it. I can't remember why.
I'm trying to remember what it means. Alright, anyway, but most of the symbols on the keyboard, I can think of a C meaning for them. Alright, and actually the dollar sign and the ampersand are definitely used on the command line.
So my bitwise OR doesn't have a gap in it.
Oh really, it's just a bar?
Yeah, it's just a line.
Okay.
Yeah.
Yeah. Both of the keywords I have in front of me have a gap there.
Hmm.
Okay, what's next on here? That's probably enough bitwise for now. You can probably just kind of follow the instructions on the project, and usually that's the easy one on the project. Not even want to do it first. All right, so then lastly we've got the sorted copy, and so this takes an array of integers, and it's also a number that tells you how many integers there are in the array, so you know how far to go. All right, so this function should make a copy of the array and then sort the copy. So the original array remains unchanged, but it's not passed in const, so just be careful not to change it. And so tester.c, when it calls that one, if I have it right here, it'll actually check and see was the original changed. So we've got some test arrays up here. We've got numbers and we've got a duplicate of numbers. And so then we can go ahead and check the sorted copy and make sure that they're actually sorted, like make sure they're in order afterwards. And then we can go ahead and see was the original unchanged. And so you just check to see if the numbers dupe is the same as the original numbers. So numbers dupe is just like kind of a backup copy here. All right. So assuming that it works, we do kind of like a spot check here, and make sure that yeah, 2 is in the right place, basically. All right, so then assuming all that's fine, we just go ahead and free the sorted numbers. So you can see that this function b here is expected to return a pointer onto the heap, and it's going to be freed right down here. So you shouldn't end up with a memory leak from having done this. All right, placing the array on the stack will cause memory errors. Yeah, multiple ones. All right, so that's that test there. Okay, the flag there. So if it fails this test right here, then we don't bother to perform that test. Okay. All right, you may potentially, if you're working on this and you haven't done the sorted copy function yet, if it just returns 0 or something, you might want to think about commenting this one out until you finish and then putting it back, or put it back. But this will cause an actual error if you just haven't finished sorted copy yet. Okay. All right, I should probably have this thing checking to see if these functions exist, like if find best is not a 0, do this stuff. But I just thought of that just now. Been using this assignment for a while. It's been a while since I wrote this one. All right, so I think that's probably about it on this thing. Hopefully it makes some sense, and you all can make some progress on this. When did I set it due? Looks like I have this due in about half a month or so. It's like the 1st today. 1st. Wait a minute.
2 weeks.
Oh, so how is Wednesday is that true? No, it's true. It's true.
Yeah.
All right. Second, sure. I get that wrong a lot. Accidentally putting these things due on non-existent days. I don't know why that happens so often to me. Because I actually do make a habit of looking at the calendar to make sure the day exists. And somehow, I've got like, it's got to be like 15 or 20% of assignments I put out end up having a non-existent date. I have noticed that occasionally I'll be out of date, and so Cal normally does a month, right? And cal-3 gives me a 3-month window like this. But if I want the whole year, I might type cal 2020 and print out this year's calendar. But that's not this year's calendar now, is it? So I think that's part of the source of my errors. Since I have a habit of typing the wrong year and not noticing, I've been trying to make a habit of typing cal-y, which prints out the current year's calendar, whatever the current year happens to be.